So L equals mr squared theta dot. Theta dot, just as a side note, theta dot's also, that's the derivative of the angle with respect to time, which is just the angular speed. What I'm going to do is I'm going to let r equal 1 over u, in other words, u to the negative 1. So this becomes m theta dot over u squared, or theta dot is equal to lu squared over m. There is a reason for doing this. If r is equal to that, then r dot is equal to negative u to the negative 2 u dot, and which is negative du dt. Let's say 1 over u squared, which is negative 1 over u squared du d theta times d theta dt. And d theta dt we have right there. So r dot becomes negative 1 over u squared times lu squared over m times du d theta. Those cancel out, and I'm left with negative L over m du d theta. R double dot is, well, taking the time derivative of this. Remember that L is a constant, as shown in a different video. M is the mass of the planet or whatever, mass of X, if we wanted to use the language used in another video. That is a constant, and so this just becomes negative L over m times the time derivative of the angular derivative of u, which is negative L over m times d theta dt times d theta of du d theta. You can always double check working backwards. The d thetas would cancel out and you're left with this, which is negative L over m times the theta dot times the second derivative of u with respect to theta. So now, let's go back to the equation of motion. We have r double dot minus r theta dot squared equals negative g mass of that central body, the sun in the case that we're talking about here since we're dealing with Kepler, over r squared. R double dot, we have an equation right there. This is negative L over m theta dot d squared u d theta squared minus r, which is 1 over u times theta dot squared. Well, actually we have theta dot right there. So this is Lu squared over m squared equals negative g mass of that central object times u squared. It does simplify nicely here. Well, at some point it will simplify nicely. We have a substitution here, so this is negative L over m times Lu squared over m. So that's that one, times d, the second derivative of u with respect to theta, minus L squared over m squared u cubed, because I have u to the fourth, divided by u, is negative g mass of sun, u squared. U squared cancels out with that u squared, which cancels out with two of those. And the minus sign will cancel off because every term is negative. So I have L squared over m squared. Second derivative of the u with respect to theta, plus L squared over m squared u equals negative g mass of sun. Oop, it is positive because we got rid of that negative sign. I'm going to isolate u, and so I'm going to multiply by m squared over L squared. So I'm left with the second derivative of u with respect to theta plus u equals g mass of sun, mass of planet X or whatever's orbiting over L squared. We can write it slightly differently. U is equal to G mass of sun times mass of X planet, whatever we're calling it, over L squared, minus the second derivative of U with respect to theta. So to solve for U, we need some equation here whose second derivative is basically a negative of the first one, other than some constant which we can tack on, and you'll see that if we let U is equal to A cosine of theta plus some phase shift plus G mass of sun times mass of X squared over L squared, if we take the second derivative, that's immediately going to drop off. And so this becomes then negative sine, then negative cosine. So U, the second derivative of U with respect to theta, is equal to negative A cosine of theta plus phi. And so if you plug that in here, it works out. So that is sort of our solution at the moment. So remember that this is 1 over r, which is 1 over r. Now this right here, this phase shift, depends upon how we define our coordinate system. And so I'm going to define the coordinate system so that this is 0. So because I'm defining theta to be 0 here. This is theta is equal to 0, as opposed to starting theta is equal to 0 some other place. It's just convenient. So this is coordinate system dependent, so I'm going to make that 0. And so r becomes 1 over all that, 1 over A cosine theta plus G mass of sun, mass of P squared, or X, over L squared. Factoring out this whole mess here, so G mass of sun, mass of X squared over L squared, 1 over, times L squared A over G mass of sun, mass of X squared, cosine theta plus 1. Remember that in polar form, the formula for an ellipse is B squared over A times 1 plus E cosine theta. That is the formula for an ellipse in polar form. So if we can connect these two, if we can show that B squared over A is equal to L squared over G mass of sun, mass of X squared, and that L squared A over G mass of sun, mass of X squared equals the eccentricity, then we have shown that the planet travels in an ellipse.